Assalamu alaikum, ladies and gentlemen, welcome back to another video. Well, this time it's a live stream. Alright, so let me make sure this is working just fine. Haven't live streamed since a while now, so please join my Discord server. You can find the link down in the description below. Live. Alright, let's go. Hopefully everything is working fine. Let's see, pop out the chat here. Gonna keep it here. If anybody have any questions, please let me know. Alright, perfect. Alright, I just want to have some confirmation that the stream is working. So far, excellent connection. No dropped frames. Everything looks perfect. Right, so let's get going, I think. Alright, let's get going. Alright, so I have actually reinstalled my Linux system. So I'm on Arch Linux KDE, specifically Cache OS though, which basically includes some very optimized builds for the latest CPU architecture, basically, of x86. Hello, Pixeluted. Welcome to the live stream. How's it going? Alright, so let's get going. I did that so I could show you my whole Linux development using vscode and of course for C++ and with Clang and CMake. So yeah, so first of all we're gonna need, let's see, so first of all we're gonna need vscode, we're gonna need CMake, we're gonna need Ninja for our build system. CMake is our like meta build system. And we're gonna need Clang for ClangD and CMake format and so on. So yeah, what else do we need? We're also gonna need CMake format, though we're gonna install that from the AUR. It just gives us better CMake formatting, and I think that's basically it, right? I think that's basically, if I didn't forget anything. Of course, we're gonna be doing Vulkan 1.4. We're gonna try to like use the latest extensions and so on. And of course, we're gonna be using the latest C++ stuff too, pretty much. Also, we want Vulkan development packages, which would basically install a whole bunch of Vulkan stuff like Vulkan tools, Vulkan ICD loaders, Purview tools, Vulkan utility libraries, Vulkan validation layers, etc. So let's go with that one. What else we gonna need? Hello, Theoparis. Hello. How is it going? Alright, so we're gonna need CMake format, which we can find in Paro. So basically Paro-s CMake format. It's in the AUR. Okay. Alright. That's the CMake format done. The other thing is the configurator. So vacate configurator. Wait a second. And that's done. Perfect. Let's go to the next thing, which is the Vulkan configurator, or like, sorry, Vulkan caps viewer. So Arch Linux. Alright, so Vulkan caps viewer, Arch Linux, Wayland, right. And we're gonna go with this Vulkan caps viewer Wayland bin, I believe. So let's go with that. If you are in Wayland, I'm currently in Wayland. If you are on X11, then you gotta go with the X11 one, so. Well, what? Oh, I gotta use Paro. Okay, sure. Yes. Yes. Well, that failed. Alright, so let's check out maybe the other one without the bin. Yeah, I do remember there was another one without the bin. Let's see. Wayland. Yes. Yeah, I think that would work. So it basically would compile it on my machine. The bin one doesn't work for whichever reason, which is interesting. Alright. Is the stream fine? It's like I haven't streamed in a while and I just reinstalled the system. So I'm not sure of the quality. Please let me know. Great. Alright. So right now it's basically recompiling Vulkan caps viewer, which would help us just see what's up with our system, like what our GPU supports of Vulkan features and stuff, and version, etc. Though of course if you're on Windows, you just gotta basically find out how to install it through the web, you know, through Firefox or whatever. Alright, so we're good. Hello, Woji Girin. Walaikum salam. Those compiler warnings. Yeah. Alright, so you got the Vulkan caps viewer 2 now. Let's see, Vulkan, there you go. Perfect. I'm just gonna pin to task manager. And there we go. So as you can see, my API version, make sure it is 1.4. Otherwise you can't. Well, you could probably follow with this tutorial anyway, even if it's 1.3. Especially for the first live streams, I'm willing to make this like a playlist kind of thing, where I'm basically porting regular samples from official, you know, repo, and porting them to like Vulkan HPP with like the latest C++ features with Hpp RAII, etc, etc. But yeah, either way, let's get going. Alright, so that's the first one. The other one, there's also render doc. So render doc. This is also very useful for debugging. And of course we're gonna be using vkconfig or Vulkan configurator. Well, apparently I can't access it from there, but I think I can from here. Right. vkconfig-gy. There you go. Do you want to download the Vulkan SD? I don't think that's needed. No. Yeah, I don't think that's needed. Anyways. And we're gonna basically be using this to get the compiler, the Vulkan validation layers without having to basically enable them in code. And that's basically it. Alright. So I'm also gonna try to pin this to task manager if possible. And yeah, that's pretty much it. Now I could quit this for now. And we're good. Alright, so let's launch right now code. So vscode. So of course I'm using the open source version here. So pin to task manager. And let's go. Alright, perfect. So let's see how we're gonna do this now. Alright. We don't need this. And let's go. Okay, so let's start with the extensions we're gonna need. We're not gonna need that much extensions. We're gonna need ClangD. And of course make sure you have ClangD. Since we installed Clang, we do have ClangD here. As you can see here, this is the Clang version I'm using. So 20.1.8. Pretty much. Okay, so here's ClangD. Trust publisher and install. And we're gonna need CMake-format just for CMake formatting. Pretty much. And also the most important extension, error lens. This is very, very useful. It basically shows all the errors in line. And what else? I think we also may need code LLDB. For that though, we're gonna need to basically install it too. So like, sudo pacman-s code LLDB, or honestly never mind for now. I think that's pretty much it, honestly. Alright, so let's actually just use this. Let's see, Control-Shift-P, and let's say CMake quick start. Oh, but before that, let's just basically restart with this, basically. Alright, let's go. I'm gonna move this to right. Do you have reason to do this on Linux machine, or this is just because you use Linux normally? Good question. Like Linux really makes it frictionless, but like you could do all of what I'm gonna do in this live stream in Windows with no problems, pretty much. So yeah. All right. So let's see. Let's see. All right. So first of all, we're gonna need to basically create a dev folder. You don't have to, and then I'm gonna create a folder for my own project here. Let's call it, I guess, Code Vulkan Hpp, I think, or just Code Vulkan. All right, let's go ahead and do this. All right, perfect. So now I'm gonna basically launch code inside of that directory, and we should be good to go. Alright, so right now I'm going to say Control-Shift-P, and then I'm going to say CMake quick start. But apparently I don't have it for some reason, huh? I should. Oh yeah, I forgot one other thing, which is the CMake tools. Make sure to have that too. I'm going to use this one. Trust publisher install. Oh yeah, alright, perfect. Now we could say quick start CMake, perfect. Here we can name our project. In our case, it's basically Code Vulkan, and of course C++ executable, yeah. And if you want CTest and CPack, you can enable them. I won't. And we could add a new preset. We could create from compilers, why not? And I'm gonna be using Clang for cross-platform, basically. Okay, cool. Now press enter to confirm your input. So the preset name, I'm gonna go with debug as the preset name, and there we go. Alright, so as you can see, it generated for me all these files. Simple main.cpp, CMake presets, CMake lists, and that's basically it. Alright, so let's start by my settings in here, user settings JSON. So first of all, I always like to say mounts wheel zoom true, and then let's see, format on save true. So basically format on save, once I save it, basically formats everything, which is great. The other thing I like to also do is go with material icons. Alright, material icon theme. Here we go. Trust publisher install. Material icon theme, and there you go. Now the other thing is the font. I like to use JetBrains Mono. Of course, these are just like appearances, you know, just you don't have to have these appearance stuff, but if you want to have the same setup as me, you're welcome. All right, so let's see, JetBrains Mono font, Arch Linux. All right, so let's go with this guy right here, pretty much. Alright, so sudo pacman -s. Yes, and we're good. So I'm just gonna make sure to restart vscode here, and now I could change my font. So let's change my font family to, let's say, what is it called? Yeah, JetBrains. My brain is lagging. It's pretty much very like late at night, so 1 a.m. I can only record at this time. Yeah, font ligature is true, and there we go. All right, is there anything else? I think that's pretty much it for my settings. Oh, I thought it was 1 p.m. for you. Nah, it's 1 a.m. Alright, so the middle of the night, let's go. Alright, so let's go back to, so the other thing that I'd like to also make sure to have is CMake copy compile commands. Yeah. Copy compile commands and make sure to set this to workspace, I think directory, I believe, /compile commands.json. So basically would make sure to copy my CMake copy like compile commands into the the root directory of my project, so clangd would work, which is great. Alright, so how are we gonna do this now? Let's see, CMake presets, and let's go here and see what's up. I don't need any of this business right here. I'm gonna remove all that. I'm gonna keep, of course, the binary directory. So the binary directory is just out/build/preset name. CMake variables. I'm gonna remove these so it works on all machines. And for my generator, I'm gonna use Ninja. So CMake generator. Yeah, I think generator. Ninja. Ninja is also cross-platform. And of course, make sure to set CMake compile export compile commands. So clangd would work. Of course, this is just setting up the IDE stuff, not really a Vulkan project just yet. So CMake export, well, actually not true, but like I guess on, probably. Yeah, I think so. All right, perfect. Let's see if we have the compile commands right now. We're basically gonna say, oops. I'm gonna say Control-Shift-P, and then we're gonna say clean rebuild of CMake debug preset. Now let's see if this works. All right. So apparently there was some error here. Let's see. Detected version of Ninja. Why? Let's just remove this output directory and try again. Because when you change like your generator and stuff, yeah, that always happens. Workspace directory. Okay, so apparently this workspace, yeah, I think it's workspace there. Apparently, yeah, pretty much. Let's go. All right, now let's try to clean rebuild. Oh, that also doesn't work. What the heck? Well, let's just look into here. Oh, apparently it's workspace folder. Okay. Alright, and let's say Control-Shift-P, clean rebuild, and there we go. Now that seems to, yeah, there you go. As you can see, it automatically copies the compile commands in the root directory. Otherwise, clangd wouldn't work, because apparently it doesn't, or it can't detect like directories like here. What the heck is going on with the mouse? I don't understand. Anyways, so that's pretty much it for that part. Now we could actually start into our own project right now. Let's just run this, and there you go. As you can see, it works. Now if I try to say clang debug, well, not clang, CMake debug, let's see, that wouldn't work because it can't find GDB in default search path and GDB. Do I have GDB here? Let's see. I don't. So let's make sure to install GDB and code LLDB. I'm not sure if I could make okay, so code LLDB is not there apparently. Fine. Let's just go GDB, please. Alright. I'm probably gonna need to restart this. Alright, cool. Now let's try debugging again. CMake debug, and let's install that. Why not? Can I install this instead? I'm not sure if it would work. Let's see. CMake debug, and no. Let's see if we can find some solution that uses code LDB. So CMake tools, vscode, code LDB. Otherwise, we're just gonna use GDB anyways. If anybody knows some other solution to make it work with LDB, please let me know. I think maybe we just have to basically open launch JSON here. Oh yeah, and then use code LDB here. Is that the case? What? Why this doesn't work? Apparently it needs cargo for whichever reason. Oh man, sudo pacman-s cargo. I think I need to basically go with rust up or rust. Let's go with rust. So it installs cargo. Because apparently code LDB needs that for some reason. Yep. Alright, let me just restart to make sure everything's fine. CMake debug. Open launch JSON, code LDB. Okay, so now that works. Cool. But how the heck do we make these configurations? Let's see. Alright. I mean, come on. Alright, very helpful. Okay, so let's just go with type LDB, request launch. Honestly, I'll just copy this configuration right here. Alright, let's go here and here. Let's do this. Workspace folder slash. For now, let's just hard code this, to be honest with you. /out/build /debug. And there you go. Now let's try this out. And apparently that still doesn't work out. You know what? Let's just go GDB for now. If anybody knows another solution, please let me know. Because like the CMake debug thing just doesn't seem to work out. So we're just gonna go with this extension instead. We don't need code LDB. We're gonna install it, and yeah. And we don't need this launch JSON either for now. And that's basically it. Now, if we actually do something like this, we put a breakpoint here and say CMake debug, it would work now. And as you can see, it works. I can see the registers and everything else, which is great. So as you can see right now, you have a fully functioning IDE inside of VS Code with ClangD and everything else. All right, so now we could actually start actual programming. How much that took? How much that took? Okay, 24 minutes to, you know, do, like in Windows it takes even more because like you have to install MSVC and all sorts of crazy stuff, and you have problems with Clang, and yeah, either way, let's go. All right, so now what we're gonna do, we're gonna create a, we're gonna say git init. Make sure to have git, and I'm honestly gonna change my default branch to main because that's the newly recommended branch name for whatever reason. And then get branch -m, and I'm gonna change my current branch to main here because that setting only applies to newly created git repos. And that's basically it for that part. Now, what we're gonna do, we're gonna create a directory called vendor or third party, whichever you name it, doesn't really matter. Okay, now we're gonna go inside of that directory and we're gonna say git submodule add. And now it's time to add the Vulkan headers and SDL3. How are we gonna do that? Well, let's see. Let's look for SDL GitHub. Here we go. Code, take that. Now I would have used CPM or VC package, but to be honest with you, I found, like at last, I found that the git submodules way is way less friction for me. But yeah, Cyber Purcell, welcome to the live stream. How's it going? Alright, so we added SDL as a submodule, as you can see, and we're also going to add Vulkan headers as a submodule. Now you could depend on the Vulkan SDK installed in the system, but I'd rather not do that. I want my project to be self-contained. We have enough like broken C++ projects with broken builds and like hidden dependencies, you know. So let's go ahead and look for GitHub here. Okay, so we're gonna go here, copy that, come here. We're gonna add another submodule into the vendor directory, which is gonna be our Vulkan headers. We're also gonna need the VMA for Vulkan memory allocations. And Loop Luminary, welcome to the live stream. How's it going? And you're not really late. Like pretty much these 30 minutes, I think we're just like set up in the development environment, like the IDE and stuff like that. That's pretty much it. We're just starting out. Like I just added the libraries pretty much right now, and we're gonna start the actual project, the actual coding. I did this just so if anybody want to follow along and they want to use VS Code like me, they can, you know, do that. So that's cool. All right, so now we're good. Yeah, as I said, I want to also add VMA. So how are we gonna add VMA? Vulkan memory allocator. So we're gonna go VMA GitHub. And well, easy to integrate Vulkan memory allocator. Let's go. And we're gonna also add GLM. All right, so let's go here, git submodule add, well, paste the link, and there you go. The last one would be GLM pretty much, and we should be good to go. GLM GitHub, and copy, come here, submodule add. Oh boy, let's go. And with that, we're pretty much done with our submodules. We have all the submodules we need. SDL for windowing, Vulkan headers for Vulkan, pretty much. Vulkan memory allocator for efficient allocations in Vulkan. And yeah, that's pretty much it. And GLM for math, basically. And that's essential. I mean, maybe we need to add like async later on and so on, but for now, this should be fine. All right, so we're gonna go to CMake list, and now we need to do this stuff. All right, cool. So set CMake CXX standard. We're gonna go, of course, with 23 version. And what else? We're gonna set CMake CXX standard required, I think, to on, and set what else? Set CMake CXX extensions, I think, to off, I believe. I do gotta check out this though. Yes, it is perfect. And standard required. And yeah, that's right, correct. All right, perfect. So that's basically it for that one. Here we could use project name if you want to, and for this main.cpp we could add it as sources instead. And honestly, I'm gonna use globe for that. Yeah, let's use a globe. So like file globe recurse, for the source code files. So let's see how we're gonna do that. Well, and wait a second. Okay. Alright, so let's see how I could do this. I can never remember how to do this. Well. Let's just go here, I think. Let's see, globe recurse. Alright, so yeah, we basically say file, I think, and then globe recurse, I think, right? And then basically we call this sources, and what else? And here I believe we could just say .cpp files, I believe, and I think that's pretty much it. And there's another variable though, configure depends, I believe it's called, like depend. So basically it makes it so that CMake makes sure to like reconfigure CMake if any file get changed. It's a new thing. Configure. Yeah, here we go. Configure depends. Make sure to add that too. And we should be good to go. Now, of course, we need to add sources here. So target add, well, target sources. And basically we're gonna go with this guy, private, and sources. Of course, this is a variable, so we're gonna do this. And honestly, let's put this here. And there you go. So basically we're taking, well, honestly, let's put it inside of src, in fact. So let's make another folder called src, which is gonna have our source code. So we're gonna put main.cpp right there, move. And yeah, let's just make sure to clean rebuild and we should be good to go. Now, of course, we need to add our dependencies right now. So how are we gonna do that? Well, let's do add subdirectory. So we're gonna add SDL inside vendor. So of course, the setup would work on any system pretty much. All right, so vendor/SDL and GLM, and so basically we're gonna have for all of them. And what else? So Vulkan-headers and Vulkan memory allocator. And honestly, I would rather go with Vulkan header GLM. Well, couldn't you use CPM since it's cross-platform too? Yes, but a lot of times I like to remove my out directory, and then basically CPM would have to like re-download everything, which really suck. And that's why I'm using this instead, like just using submodules. And that's pretty much it. Now we could just say target link libraries and project name private. And we're gonna basically go with SDL. So SDL3, GLM. Right, well, GLM. I think there was some interesting thing about GLM, but let's add it anyways for now. Vulkan headers. And we also gonna need, honestly, let's link Vulkan headers first before SDL. Okay, and then we're gonna go ahead and, well, for Vulkan memory allocator, I need to check out on the file. Hold on. So if we go to CMakeLists here, what I like to do to find the target name, Control F, add library, and then I look for where's the things here, and here we go. All right, perfect. Now let's add that here. And what else? So for GLM, let's see, let's do the same thing. And let's look for add library. And apparently there's no add library, huh? Oh, GLM header only, huh? I don't know. I don't remember even. I guess this may work. Let's see. Here we go. SDL is actually, it's GLM. All right. Okay, so SDL right now is configuring CMake stuff. Great. And let's see, because I remember there was some problem with GLM in CMake. For some reason, I don't remember exactly what, but yeah. Either way, right now SDL is being compiled from source code. The other nice thing about compiling everything from source code is that you could actually, you know, let me show you some interesting trick if you're not seasoned enough to already know this. But like you could do something crazy like this. But of course I need SDL first. All right, so SDL 3/SDL.h. If you have broken includes, make sure to watch my previous part of setting up the IDE, clang stuff, and compile commands. Otherwise it wouldn't work for you, right? As you can see with the compile commands.json in the right place, everything is working perfectly fine. All right, so SDL init video. And let me show you a little trick. Well, I need to do some other thing, maybe. Like, let's say SDL log hello from SDL. For example. Okay, cool. Now let's do something like this. We're gonna put a breakpoint here, and let's say Control-Shift-P, CMake debug. And let me show you some magic. Okay, step into, and here we go. We are in the actual like SDL code, and we see exactly what SDL is doing right now. And once it's done, it's back. You could basically go inside of any function using step into. You can step over, continue, step out, etc. All of these cool stuff. All right, and that's basically it. All right, so now we're gonna actually be using SDL3 main callbacks. Why? Because, well, this would work everywhere. I don't truly care that much about cross-platform, but I just like my code to be architectured correctly for any platform, right? But yeah. So in case of other platforms in the future support, you know, Vulkan 4 and all the features I like, then yeah, it would work. Or if someone would want to patch it and like adapt it to their system, it would be very easy. Anyways, who cares? Now, what we're gonna do? Yeah, I need to look for the documentation of main callbacks. Let's see. All right, let's see. SDL3 main callbacks. All right, main use callbacks. Well, readme main functions. Here we go. Go on. Is the stream fine? Yeah, seems like. I don't know why the network here sucks. Bruh. I don't need these. Is it a SDL thing maybe? Yeah, it's probably, yeah, it's like the website is slowing down for some reason. Maybe they have some problem. Alright, I thought it was my network for a second there. Alright, cool. So let's see what we got here. Alright, so we're basically gonna copy this guy right here. Gonna paste it here. And yeah, basically. And we're gonna remove this main function stuff because that would be handled by SDL, because basically there's differences in the main function, you know, in web using imp scripting, in Android, etc, etc. SDL could handle all of that for us, all those changes. All we need to do is to basically define these functions right here, like this, and we need this guy to this guy and this guy. Alright, so we basically need to define all of these, and of course I'm gonna make my own class, app class. Right now I think I'm just gonna do it inline, to be honest with you, to keep things simple if possible. Alright, let's see. I'm gonna try, if possible, I'm gonna try to keep like the whole code in one file, because like, at least for me personally, I find tutorials that like make the code, separate the code into multiple files very annoying when you're just learning out. You just want to like see everything in line in one single file. I'm not sure if that's gonna be possible, but we'll see. Alright, so class app, perfect. So how are we gonna do this now? So we're gonna basically allocate application here. So how are we gonna do this? Well, auto app is equal to new app, pretty much. And that's gonna be it. And now we're gonna say app state is equal to application. So basically SDL gives us 4 functions: init, which runs at the start of the application; iterate, which runs every frame; event, which runs on every event; and quit, which runs on the end of the application, right? Right here in init, we're going to create a new class app, which basically would get allocated on the heap, because otherwise if we allocate it on the stack, then once we are done with this function, it would get destroyed, and so we would have a dangling pointer in app state, which is, of course, we don't want that to happen. Right? And here, of course, in SDL app quit, we have to basically delete app state. And well, first of all, let's actually grab the application. So auto app is equal to static cast app pointer app state. So we're basically going to cast the pointer to the app, and then we're going to basically say app quit, and then we're going to delete app, and that's basically what we're going to do, I think. Isn't it? I'm thinking, yeah, pretty much. And here we're gonna actually say app init. We're gonna return app init, pretty much. Right. And basically we're gonna take the app on every single function here, and we're gonna return app event, and of course we're gonna pass it the event. And yeah, we're basically wrapping these callbacks into one class called app, since we're in C++, so we don't need to have a global state around there. Cool. So here auto app, and then app iterate, and we're good to go. Well, of course return here, and yeah, pretty much it. That's pretty much it. All right, cool. So now we need to basically grab the init function here and the iterate function here and the event function here and the quit function. Now, of course, SDL app result would be returned by this guy, and by this guy. And we don't need the app state in here because we're using that already to get the application, basically. And of course quit would be void. Otherwise you could also use the newer syntax of C++, which is basically just say auto, right? And then basically do this. It's really closer to Rust and other modern languages, but yeah, like you could do this basically. Same thing here. And there we go. Alright, so for char, like int argc, char argv, we could do something interesting. We could use span, actually. So basically init here, instead of this, we're gonna take this guy and we're gonna make an std span here. Span args. Oh yeah, one thing that is very annoying is that ClankD would try to auto-include headers for you, and sometimes it works, but a lot of times it's just very annoying and it like includes the wrong headers and so on. So I'm gonna pass in an argument to actually don't allow that anymore. But yeah, does that result is any difference than just looking different auto return? Currently it's not really any different, it's just looking different. The one nice thing is that like it aligns well, you know, and like when you go with callbacks, you're actually gonna do a similar syntax too, at least for now. There is some other advanced features, but I'm not gonna get into that for now. Alright, so std span char, and then this is basically args, okay? So instead of passing argc and then a double pointer argv, we're just gonna pass a span. A span is kind of like a vector, but like you don't own those arguments, you don't own those strings. Because like in a vector, you basically own that list and you should destroy it. I mean, we could create a vector out of those, but that sucks. Why allocate? There's no need. So these are just given by the system, and then you just pass them along. And like basically, you can think about span is just like a regular pair of basically a size and a pointer. That's pretty much it. Nothing else. It doesn't allocate, it doesn't do anything else. Alright, so that's basically it. Basically modern pointer to array. Yeah, exactly. Alright, so also another nice thing about spans is that they could basically take anything. They could take a pointer and a like a size number, and they could also take a vector, they could take an array, they could basically point to anything, right? And they could also point to a slice of a vector or anything like that, right? Anyways, so the first thing we're gonna pass in is argv, and the second is argc here. And we should be good to go. Now argc wouldn't work, and if you say quick fix, we can insert an explicit cast to size t, and there we go. So as you can see, we just gave it the pointer, which is the first, and then the count, which is argc, and that should be good to go. So these are private members. Let's make sure to make them public here, and there we go. Alright, so let's make sure we have a semicolon here. And here quit. Oh well, let's remove that app state and let's give it a result here. And that's pretty much it, I think. So alright, cool. Cool. Yep, cool. Alright, so what we're gonna do in the initialize function? Well, we're gonna call SDL init. SDL init. Oh yeah, let's first of all take care of that business of auto including that really sucks. Let's go to syncs JSON, and I could never remember this stuff, so let's look for it. What is it called? Okay, let's see. Yeah, ClankD auto include. No, auto include. Or disable auto include or whichever. Let's go with disable auto include. Let's see. I think this one. I've seen it. Yeah, there we go. Oh my god, this one. All right, it's very annoying because a lot of times it actually imports the wrong header, or it imports the same header multiple times, which was really annoying to me. Already do init SD. Pretty sure the main callbacks already do init. No, it doesn't. You should do it yourself. It's just that if you actually, let's say, called some other SDL function, like let's say SDL create window, it would actually implicitly initialize SDL for you, but you'd rather do it yourself explicitly, you know. Though on the SDL app quit, you don't need to call SDL quit because, well, it would do, like SDL would do that for you automatically, you know, because there's nothing fancy about quitting. But SDL init takes a parameter of like what you want to initialize. Do you want to initialize only the video subsystem, or do you also want to initialize, let's say, gamepad stuff and audio, etc., etc.? So basically, you could handle a lot of things there explicitly, like the error handling, and also you avoid the lazy loading, you know, penalty. Because, like, for example, create window, if it SDL is not initialized yet, then your create window would stall until SDL is getting initialized. But yeah. All right, so let's go ahead and say SDL init video here. Now, the problem that we're gonna have here is that this guy, like all the SDL functions, returns like some kind of way to tell you if there is an error. For example, here it returns a boolean, either true or false. Did the SDL library get initialized correctly or not? Now, what you would do in C is that you would say if not SDL init, then basically, well, I don't know, SDL log, yeah, and then you're gonna say cannot initialize. Let's actually include log here. SDL log, okay. So cannot or fail to initialize SDL, right? And then you're gonna do something like this, and then you're gonna make sure to get the SDL get error. So SDL get error would tell you like why this failed, but it wouldn't tell you what's exactly have failed. So we basically do both right here. Fail to initialize SDL, and we tell it exactly what failed. And that's basically, and then we could, let's say, return SDL app failure. And then of course here, if everything goes well, then we're gonna say SDL app continue, telling SDL that we're all good, you could continue on your way. So yeah. All right, so that's great. Now if we actually run this, what the heck? In the find reference to SDL app quit. What? Wait. What happened? Do I actually have to have like the CPP and header stuff? Weird. I mean, maybe. That's weird. I mean, let's try to do that. app.hpp, right? And then you would basically have this, then this, then of course you would take the init and log func, well, just the init here. Yes, let's go. And for this definition, we're gonna take it out from here. Oh, my bad. Oh my god. All right, hold on. I forgot. I need to actually define these two. My bad. All right, so let's keep it in one file. My bad. All right, so SDL app continue here for the iterate. And then here for the event, you're gonna also return SDL. Well, for this one, we're gonna switch on the event dot type pretty much, right? And then we're gonna basically case off SDL event quit. Then we're gonna basically return SDL app continue. Well, actually, success, right? So as to quit the application with a success code. And yeah, I think that's basically. Otherwise, if we got some event that we don't want to handle, then we're just gonna ignore it and we're gonna continue the app. Hello, Slav. Welcome to the live stream. Thank you so much. All right, so return, and there we go. And I think that should do the case, right? Here in quit, we don't have to return anything, and that's, yeah, all right, perfect. Now it's working out. Great, lovely. All right, so now, instead of handling all the errors like this, like every single SDL call, you would have if not and so on, we're gonna make an actual SDL exception for this class, SDL exception, you know, and then it would basically inherit from, let's say publicly, from std runtime error. Right, and then we're gonna say SDL exception. Well, of course, this should be public first of all. So SDL exception constructor, and this would take a string. So I guess we could say std string view message, right? And let's see. And of course, we need to basically initialize runtime error base class here. And what we're gonna do for that, we're gonna use std format, which is the new format stuff, which comes from the format header right here. So std format, we're gonna do something like this. So this is basically a placeholders, right? So these are placeholders for putting something. Now the first thing that we want to fill the placeholder with is our actual custom message. The second is going to be SDL get error. Now just keep in mind the std format does allocate, but yeah, if that matters to you. Other than that, we're good, I think. Did I miss something here? I think maybe. Nah. What? Something is strange going on here. Okay. Let's do it like this. All right, perfect. And there we go. And that's pretty much it. Now, instead of doing this business, what you're gonna do is just say throw SDL exception failed to init SDL. And since this is also one line, you don't need these brackets like this anymore either. You just like that. So that's pretty sick. Let's just make sure everything's running. All right, cool. Now let's actually try to create the window. All right, so regularly in C, what you would also, let's just remove this SDL log here. Now, regularly in C, what you would do is to create a window, you would basically create, let's say, an SDL window like this, you know, row pointer. And then you would say window, well, let's actually call this window with like this for the member function, like the member variables or members basically of the class. I'd like to basically have this suffix, right? Just like Google style, but yeah. All right, cool. So what we're gonna do is window is equal to SDL create window. Now the title, let's say code Chaco, the width, let's say 800 for example, 600. You could choose, of course, whichever you want. For the flags, we're gonna go with SDL window resizable and SDL window Vulkan. Resizable only included if you want the window to be resizable, pretty much. Really that simple. Otherwise, now we're gonna check if not window, then we're gonna throw SDL exception fail to create window. Although C++ has many components, I prefer C because it's simpler, but C++ is also very useful for large projects. I see. Yeah, it's what can I say? It's like, yeah, C++ does have a lot of crap going on, right? But you could just stick to the latest practices and you'll be good. It's not as easy as C. It's like, you know, C++, it's actually very easy to get wrong, but like you can't get very wrong with C basically. But yeah, it's like at least master C first, so you understand how everything works, and then you could hop on into C++ because the C++ ecosystem and tools that it gives you is very, very nice. Alright, so Silicon Jiller, welcome to the live stream. What is SDL? Can someone explain? SDL basically helps us create windows in a cross-platform manner. It's like otherwise we're gonna be using Win32 API on Windows to create a window and to handle input and so on. Like for example, let's say we want gamepads, then we're gonna need to look into the Windows API to see how we could actually use gamepads on Windows. On Linux, we gotta look into X11 and Wayland and implement all of that crap ourselves. But on SDL, you just say create window and it handles all of that garbage for you pretty much. Same thing with even the main function. Like every single platform have a different main function. Mscripting, for example, goes even worse. Like you have to basically hook into its own main loop crap, right? But if you use the main callbacks of SDL, it's already handled for you using the event function here, the event callback here. Well, SDL app event. And a whole bunch of stuff. Let's say you want, for example, to load Vulkan library. Then you need to use Lloyd library API in Win32 basically. And then in X11 or like Linux, you gotta use DL open function. Yeah, there's just a whole bunch of stuff that we have to care about in terms of cross-platform business. But if we use SDL, we only care about SDL, right? And SDL cares about everything else for us. Steam using SDL too. Yep, pretty much. All right, so maybe make it hidden window since creating device swapchain stuff takes time. Yeah, that's true. Thanks for reminding me. So we basically gonna make it hidden until we're done initializing everything. Hello, Yo-Yo Man 3D, welcome to the live stream. All right, so that's good. Now, if not window, which means that we weren't successful, then we're gonna say failed to create window too simply. All right, now this would work. But since I'm on Wayland, unfortunately the window, although it's got created, it wouldn't show up. In Wayland, it only would show up until you basically start, you know, rendering into it pretty much. Well, actually we need to say SDL show window at the very least though. Window, okay. So at the end, after we initialize everything, I'm gonna say SDL show. As you can see, it's right here. It's created a new window called Code@Chaco, pretty much, right? But it's not displayed since we're not rendering yet. On other platforms like Windows, create window would already give you a window up and running. So, but yeah. All right, so now this is fine, but it's not the best. In C++, we have better ways to do this, because right now what you gotta do is to make sure that on the deconstructor, once like you quit, you have to also say SDL destroy window here. You know, window. But instead of and even worse is that if you happen to throw some exception after the window got created, the window wouldn't get destroyed properly. And so you have a little problem right there, right? So how I could solve this in C++ 23, or in fact even in C++ 14 or 11, like when we got smart pointers. I'm not sure which version exactly, but anyways, so how are we gonna do this? Well, we're gonna use std unique ptr. So we could say std unique ptr SDL window. And then here we gotta say SDL destroy window. Well, we gotta give it the decal type, the type of SDL, well, reference to SDL destroy window. When I'm creating window XCB on Wayland, somehow windows show up IDKY. Well, on XCB, so XCB uses X11, right? But I'm on Wayland, which is the latest kind of X11 replacer. Essentially, it's like the new kid on the block, pretty much. But XCB also shows up, like the window shows up the moment you say SDL create window, and of course show window. Yeah. Only on Wayland, it's like you need to first of all render into the window, then it would show up. So yeah, that kind of tripped me off for like hours of debugging. But yeah, there you go. Okay, so that's basically it. Now here, instead of window, we gotta say window.get, because right now we have a smart pointer. I'm using Wayland 2. I use xcblib for window creation. Well, since you're using xcb, even if you're on Wayland, it's gonna use xwayland, right? So it's kind of like just emulating X11 on Wayland, and that's why it worked. Okay, cool. Call to implicitly default constructor of app. Yeah. Let's see. It's like, yeah, let's actually create a like constructor right now. I'm using X11 of FreeBSD. That's pretty cool. All right, so let's actually create app here, default constructor, and let's basically say window, right? And here we could say null ptr, comma, SDL destroy window. So we're just gonna give it like the PTR, the pointer to the constructor essentially. And what the heck is going on here? Let's see. All right, cool. Now here, instead of equal to, we gotta say dot reset. So we're basically initializing the unique pointer with nothing, no PTR, and then we're resetting it here to the new window. Pretty much, and that should work. I don't think we even need this anymore. Alright, cool. And that's basically it, but it kind of sucks. Even this method kind of sucks, because like you have to give like the deconstructor in the constructor and so on. That really sucks. So instead of doing this, what we're gonna actually do is create a struct which is gonna destroy our window. So window deleter, and it needs basically an operator of, you know, call operator. And this call operator would kind of be like SDL destroy window, which basically takes an SDL window. And then what you would do is, well, auto here. What you would do here is say SDL destroy window. All right. I think that would work, right? Let's see, public, and instead of now passing this stuff, we're gonna pass the deleter, the window deleter, to the unique PTR second argument. And now we don't need this anymore. In fact, we shouldn't do it. It wouldn't work. And yeah. And there you go. It's cleaned up. Great. But we know that we're gonna need such a wrapper for a whole lot of other, you know, objects, SDL objects. So instead of just, you know, making another object for every single one, like let's say window and then render deleter and so on, that kind of sucks. We're gonna use generics. So we're gonna say template type name T, right? And we're gonna go with auto F, right? So here we got basically a type T and the function F. Here it could be anything, because I said I used auto here. And instead of window, I'm going to call this a generic PTR deleter, right? So PTR deleter. And here it could be any T instead of SDL window, it could be any T. And here it could be any F instead of SDL destroy window. And of course I'm going to call this PTR. And that's basically how it goes, right? And then I could make an alias for window. Using window is equal to, are you going to use Vulkan H or Vulkan HPP? Vulkan Hpp RAII, so like the latest thing, pretty much. And hello to the livestream, Lermog. Okay. So using window is equal to PTR deleter. Cool, until you get cryptic compile messaging screw-ups. I mean, I like, the trick is to not get them in the first place. Alright, so SDL window here, and then SDL destroy window. It's like in C++, it's kind of weird. It's like once you get used to it, you don't even need to read the errors anymore. You just know what's wrong from the error form. Let me open up the window. Not an SDL window though, the real window, but anyways. Alright, so here we go. Okay, so now we're pretty much good to go. Now instead of using this business right here, we could just say window, like using our type alias. And yeah, what's going on here? Whoops, not PTR deleter. So you're gonna say std unique PTR SDL window, comma, the deleter basically. Wait, what's going on? I probably missing something again. Let's see. Did I? Yeah, let's include memory. And there we go. Perfect. Now you can notice that there is a pattern here. We're passing SDL window here to unique PTR and passing it to this PTR deleter generic stuff. So what we could also do is using PTR is equal to this. Right? And then we could make another template here. And basically we would pass in T to here, and then finally the F here. And that's basically it. And now instead of this business for window, we could just say PTR SDL window, SDL destroy window. And there you go, done. Pretty much. Now, wait, I hope you don't forget to add explanatory text because you understand what's going on now, but in the future only God will understand. That's for sure. This kind of RAI is cool for stuff like Windows handles. We're going to be using RAI for everything because we're going to be using also exceptions. And it's very important to get RAI right when it comes to exceptions. Otherwise, your resources wouldn't get destroyed properly. Oh god, are we writing the STD implementation? Maybe. But like, this is, I'm not going to be abusing templates today. This is just for this single part right here, pretty much, and that's it. Though for F right here, this could be anything, which sucks. Now we have two options. We have either to use the new C++ concepts, which is like Rust traits, if you know Rust. Or just since we know this should be like a regular C pointer function, instead we could just use that pretty much. Keep it simple. So to do that, what we're gonna do is instead of auto, what we're gonna do this, right? To make it a function like a regular raw function pointer, which basically takes a T pointer, and I think that's basically it. Wait, void. Well, is it void? Right, yes, it is void. Well, yeah, pretty much. So that's pretty much it. So we're basically here making sure that F is a function pointer that takes in a T pointer and returns void. In this case right here, it would be F would be SDL destroy window, and the T would be SDL window, basically. And that's simply it, right? So we're gonna do the same thing here pretty much, and we're good to go. All right, so that's it for the PTR. We're done there. Perfect. Now let's go to the other business. Right now we actually need to use Vulkan Hpp RAII. So how are we gonna do this? Well, actually before that we need to load the Vulkan library using SDL. So how are we gonna do that? Well, if not SDL Lloyd library, well, Vulkan Lloyd library, right? So by the way, ClankD automatically, includes for me the headers when I say enter on that. So make sure to add all of these basically. So that's cool. All right, so Lloyd library, we're just gonna say null PTR, basically telling SDL to figure out what is the path itself, depending on the platform. And yeah, that's pretty much it. Now let's just say throw SDL exception failed to load Vulkan library. Or maybe, implement your own software render a CHAD. So yeah, that's pretty much it for that part. And now we gotta get the vkget instance proc addr or address, which would allow us to load all the Vulkan functions from the driver. And let's see, so auto vkget instance proc addr is equal to, let's see, static cast, I believe. True, maybe we should call register window class xw ourselves. All right, let's go. pfn vkget instance proc addr, and let's say SDL Vulkan Lloyd library. Well, get vkget instance proc addr, and there we go. Though I'm pretty sure known type name, huh? Well, let's actually include as Vulkan HPP Vulkan/Vulkan RAII.hpp, and there we go. Well, of course, static cast wouldn't work here. We need reinterpret cast pretty much, and this should work out. Now what we're doing here, we're basically, after loading the shared dynamic library of Vulkan, which contains all sorts of cool stuff, we get the vkget instance proc addr from it, which on SDL it just returns an SDL function pointer. Then we cast that to a pointer function type of vkget instance proc addr from our Vulkan HPP header. And then we're basically ready to start, loading functions here. But of course, we're not gonna do that on our own. We're not drunk. We're gonna be using Vulkan Hpp RAII to do that for us. By the way, you don't need to be using, what is it called? Volk here, because Vulkan HPP would do the job for us here. Oh, we will not be using SDL GPU. Yeah, we're not. I didn't use SDL GPU anymore because I wanted to do video stuff with FFmpeg and other libraries, and sadly SDL3 GPU is not supported. So I thought instead of limiting myself, I would just go back to Vulkan pretty much, because I would like to maybe make a video player in the future, or who knows, maybe even a video editor. And Vulkan is pretty much the only option here. So yeah, of course with FFmpeg. Unless of course if you want to use FFmpeg just using software, but I want to use hardware, using Vulkan decode and zero copy, which means everything stays in the GPU instead of going 2 trips between the CPU and GPU. But yeah, either way. All right, so that's vkget instance proc addr. Now let's actually create a vk RAI context. So how are we gonna do this? vk RAI context. Now the problem is the RAI objects, you have to actually construct them inline, in the constructor, which we can't in this case. So I'm just gonna make it std optional right now. And there we go. And alright, so now we're gonna in place back. So after we get the instance proc ADR, we're gonna say, well, context dot in place vk get instance proc ADR. But of course this wouldn't work, because we need to actually define some variables, some constants, or maybe actually macros, yeah. And what those macros are called, let's go to context here and hold control, click on it, and let's go. Alright, so we're gonna basically define this to 0 so we can get access to this second one here. So we're gonna basically make sure to define this to 0. And we're gonna take this guy and also put it here, because why not? And now this should work. As you can see, we don't get that error anymore, and that works out just fine. Lovely. Also, you may want to define vk no prototypes so we don't accidentally call some raw Vulkan function. And yeah, I think that's pretty much it. And so now this would basically go ahead and load all of these Vulkan functions for us. Like for example, enumerate instance version. So this is the Vulkan version we have. So what we could do here is, I do remember there was like a way to get the, wait. Like if we say SDL log std string, I believe, or like toString. Yeah, I think it was maybe, but I don't think it would work here. Yeah, no, it wouldn't. I wonder if there is a function for that. Hold on. So like Vulkan Hpp toString version. I think you just gotta, do it manually. Yeah, pretty much. Just gotta say, I guess, version major. Yeah, let's go. Vulkan version, comma. So what this returns again? An signed int. Okay, let's change that to that dot that, and let's just say vk minor version, or version minor actually, yeah, Vulkan version, and there we go. And let's go. So this should, if Vulkan is loaded properly, yeah, as you can see, it returned 1.4 here, so which is like the latest Vulkan version on my system, which is great. Alright, so we don't actually need this. We want to use the context to actually create an instance. So how are we going to do this? Well, again, std optional vk RAII instance. Now instance, okay, let's go. So for the instance, we're gonna need the extensions, the required extensions to enable like the Vulkan surface extension and Wayland. So how are we gonna do this? Well, we're gonna make basically first of all a uint32 for the instance, like required extensions count. The instance required extension required. This part of Vulkan boilerplate is very fun. Yep, it is. The cd span. So here we're gonna use span again. So required extension, well, instance required extensions. We're gonna use SDL Vulkan get instance extensions instance required extension count, and here we're going to pass in the instance required, well, the actual count here. There we go. Perfect. And that's basically how you get the extension. So basically SDL Vulkan get instance extension return to me a pointer to a list of strings, essentially. And then it also gives me the count through a out parameter. And then I'm basically using both of these, the pointer returned and that parameter, in the std span. And that's basically it. Now we're also going to need the vk instance create info, and before that we actually need the application info. So instance application info, or honestly let's just go straight into doing, yeah, let's just go straight and say instance dot reset, actually not reset, in place. Yes, in place. And what we're gonna do here is, first of all, we're gonna need the context, and second of all, we're gonna need the instance info. So how are we gonna do this? Well, vk instance create info. Whoops, there we go. And we're gonna construct one, and then we could use the function setters basically. So set extensions, enabled extension names. And we're gonna basically pass in the instance required extensions, and there we go. Now no matching, well, since this is std optional, we gotta make sure to unwrap that optional by doing this asterisk, or you could say dot value. Just make sure that it does have a value, but yeah. And there you go. You're pretty much done with that case. And let's also set the p application info, and for that we're gonna say vk, wait, hold on, set application info, vk application info dot set API version, and for that part you're gonna say vk API, well, like 1.4, or how do you do that? API version, yeah, 1.4, API version 1.4. And there you go. Now of course take an address to that, and there we go. So this, like, if you're familiar with Rust, this is kind of like the builder pattern basically, and everything is pretty much inline. Like, you could set some other stuff, but right now I only care about setting the API version to 1.4 and setting the extensions to this, like the required extensions. And yeah, that's basically it. Now let's make sure we're calling the right function here. And how we're gonna do that? Well, we're gonna grab the Vulkan, well, that doesn't work apparently. All right, let's say vk-config gy, and there you go. Don't show this. No. All right, cool. Now let's go to the API dump here. So we're basically activating an extension, or sorry, like a layer called API dump. And if we run this now, it's gonna tell us which raw Vulkan functions we're actually calling. And that apparently doesn't seem to work. Hold on a second. Wait, let me actually call it from here instead. Yes. No. Let's set API dump, and let's try again. Okay, so now that works. Perfect. Now as you can see, it tells me all the Vulkan functions I'm calling, and even the return code and everything else. Which is cool. And here we go, the extensions that we actually enabled. It's the surface and the Wayland surface, which is great. And that's basically it. All right, so now let's go to the next thing, which is to actually get a Hpp RAII, I think, PhysicalDevice. Well, yep, pretty much. Actually, before that, let's actually create the surface. Yeah, let's create the surface KHR. So surface, and honestly, we're gonna create the surface first. for all of this business, I think. And then after creating the instance, we could actually create the surface. Well, how do you... Yeah, that's good. All right, so let's go with surface dot... Well, in fact, we need to use SDL for this. So vk surface khr raw surface. Right, so we're gonna say if not SDL Vulkan create surface. Here we pass in the window, which is like window.get, and here the vk instance, which is basically instance here, and the allocation callbacks null ptr, and finally the raw surface. So if that doesn't work, we're gonna throw an error. So throw SDL exception failed to create surface, and there we go. So here we're actually dereferencing twice the instance. Why? Because we have an std optional, so we unwrap the std optional, and the second thing is we unwrap the Hpp RAII instance. Why? So we could actually get a raw handle for create surface. Otherwise it wouldn't work, as you can see. And that's pretty much it to create the surface. Now we could get the physical device. So let's do the same thing for the physical device. Physical device. And there we go. Now for the physical device, how are we gonna do this? So you're supposed here to select a physical device depending on the surface, but we're just gonna ignore this for now and just select the first physical device, which is most of the time fine. So auto physical, well, actually not that. Let's say physical device dot in place. Yep. And here we can give it the instance, and what else? And we need to unwrap the optional there. And what else we need? Actually, no. Wait. In place. Actually, we need to say instance.enumerate required, like enumerate physical devices dot front. And there we go. Perfect. So we're basically getting the first physical device, and that's basically it. Next up is the actual device. So we're just gonna copy this, paste here. I'm waiting for a nice window and then I can sleep. Well, that's gonna take a long while. Device. Because Wayland wouldn't actually do that until I'm done with the whole rendering, at least clearing the window with a color. So yeah. So that's the device. Alright, so how are we gonna do this? Well, let's see. Device.inplace. So this would basically require the instance, and then a vk device. Well, device create info, yeah. And we're gonna set the pq create infos. So set q create infos array proxy. And for this one, we're gonna go with vk q create info. Well, I'm gonna do this and then set queue priorities. Well, here we actually need I don't think we can give it, well, hold on a second. Actually we can, hold on. Maybe we can. I don't think it likes it. Well, let's see what's up first of all. Wait, what's going on here? This is weird. set q create infos, and then here we're gonna say vk q create info. Wait, what? It doesn't seem like it's liking it. So let's do it here. Q create info, I guess. And then pass it here. No matching member function for call to in place. Well, actually not the instance, in fact, the physical device. Okay, there we go. Now, was that the problem all along? Let's see. Well, no. Alright, fine. So now what we're gonna do is q create info dot set q priorities. And let's see if we could just say this, but apparently not. So let's just grab the queue priorities too. Or maybe we could even say this. How about that? Nope, that doesn't work. Alright, fine. So let's just say let's make a float array essentially. So queue priorities. Well, just like that. Does that still happen? Let's see. If I do this and then I do this. Actually, it works. I don't know why it didn't work there. Weird. Okay, how about this one then? No, this one doesn't. Alright, so that's pretty much it for the device, I think. Yeah, the other thing we need is the actual extensions. So let's set the enable extension names to vk swapchain khr. Well, hold on. What? No. vk swapchain khr. Well, khr swapchain. Swapchain name, extension name. There we go. And there we go. Perfect. We're just basically enabling the swapchain extension in the device, and that should be it for the device. Perfect. And finally, we're gonna need the queue for the context. Queue. And for the queue, we're gonna do queue dot in place. Here we can give it the device. So, and then the I believe like this, yeah. So queue family index and the queue index. And that's pretty much it. And we're done with the context to some degree. Now you can notice that all of these optionals sucks. So what we could do instead is we could group all of those objects into one struct called context, VulkanContext. Right, and basically would group all of these objects, right? And now we could actually say, like, hold Alt and select all of these and remove all these optionals. Do the same thing with this. The Vim users are probably laughing at me, but that works. Alright, so that's pretty much it. Cool. Now, we're just gonna make a little, or do we actually need to? Let's see. So now, instead of doing that business, what we could do, we could just do one std optional that groups everything, VulkanContext. And there we go. Now we need to put all of these code in there. So how are we gonna do that? Well. So we gotta use the constructor, of course. And how are we gonna do that? Well, the context would be made from the vk get instance proc ADDR. And we would get that here. So pfn vk get instance proc ADDR. And that's how we're gonna initialize the, hold on. That's how we're gonna initialize the context. Now we need to initialize the other ones too. Now to actually do the instance one, we have some more involved stuff. We have this part here. So we could make a little like static helper essentially. So we could say private static create or make instance. Okay. Now instance would basically require vk RAII context. Of course, make sure to have it as a reference here. And then we could basically take this code right here that creates the instance and put it here. And now we don't need this in place. We could just initialize in place and then return. And we don't need this, the reference here anymore, because we're taking the actual RAI context directly. And yeah, so here we could say auto, and then we could say that this returns an RAI instance. And well, there we go. And that's basically it. Otherwise, if you don't want this helper, at least in make instance, what you could also do, you could let it pass in the extensions. So instead of that, you could say std span of of chars, const chars, required extensions, and then you would just take this instead and remove this business and just do it here pretty much. Well, bruh, I guess like that. Did you mean context? Yep, I did mean context. And instance required extensions. Yep. And there you go. But honestly, that sucks. That sucks right there. All right, nah. Now let's keep the static, please. It's much cleaner. So we're just gonna say this instance make instance, and then here we're gonna pass in the context. Oops. And there we go. And that works. That works. Next up, we're gonna need the surface business. So we're gonna take this business right here and create another static helper. So static auto, well, make surface vk RAI. What we're gonna need is the instance, of course. vk RAI instance. Sorry, surface kchar here. And there we go. And of course we're gonna need the window too, so we could just pass in a row pointer. We don't need any fancy unique PTR or whatever here because we don't want to own the window. Unless if you want to make it explicit, like you could store a shared PTR to make sure that the window doesn't get destroyed before the VulkanContext, but we don't need to here since we're guaranteeing that the lifetime of, you know, the surface would stay until the app is done. So we're good, we're fine. We don't need that business. So, all right, so here we could just pass in the window directly. And here the instance, we only need, I believe, one dereference here. And that's pretty much it, I think. Now we're gonna do the same thing with surface here. Oh wait, what the heck? Not here, here. Comma. Surface, right? Well, surface. So make surface. Well, what the heck? Make surface. Here we pass in the instance, and here we pass in the window. Now the window, we gotta get it from outside. And actually we don't need this required extensions anymore, at least for now. And we only need the SDL window here. And that's basically, in fact, even the get instance proc ADR, if we really want to. Should we do that? I mean, if we want to keep all the logic inside, then yeah. But nah, let's just keep it like that, fine. Alright, so that's pretty much it. What else? Finally, we're gonna need to initialize the device and the queue. And well, the show window should be last. So how are we gonna do this? Well, we're gonna copy this part. Well, actually, the physical device first of all. Yeah, the physical device. And honestly, this part right now, well, let's just make a function for it too. Why not? So static auto select physical device. Now, generally, would use the surface too to select a physical device. So we're gonna pass that. Alright, so the RAI instance here, and then the Vk RAI surface. We could implement the surface check-in later on, but for now let's just pass it in. And this would give us the Vk RAI physical device. And there you go. So for the select physical device, we can go with this part, right? Well, actually, it's just too simply this, right? So we're gonna return this, and here it's gonna become this, and well, dot. All right, for now it's pretty simple. Later on, we could expand it. Next up is the device. Well, here let's make sure to actually say physical device. Well, select physical device. Here we give it the instance, and here we give it the surface. The nice thing also about this is that the dependencies are pretty clear, which is great. Anyways, so right now we're gonna need another function called create device or make device. And make device would basically be this return, and we don't need device to in place. Here Vk RAI physical device. I believe. And then we just need to vk RAII device. I think. Yep, pretty much. And there we go. So now here, gotta say device, make device. And we're gonna pass in the physical device here. And the last one, at least for now, is the queue, which is this guy. So static auto make or get queue in this case. vk RAII device, and honestly, well, for now I could just go with that, fine. And this would go ahead and give us a RAII queue, and this would basically go ahead and say return the device, comma 0, 0. Well, device like this. And there we go. Now the last parts of the puzzle here is queue. Well, oh my god. Well, what the heck? No, device. Well, actually get queue device, yeah. Well, let's make sure that this is reference here. What else? Oh yeah, well this should be vk RAII surface khr, and we should basically return instance, well, oh, I guess maybe just the raw surface, or what? Wait, what the heck? Oh, what? No. Wait. Instance, comma, raw surface here. And there we go. Alrighty. And we're done with the VulkanContext here. Just add a semicolon, oops. Add a semicolon there. And we're good. Now we could remove all this crap up until I think here. And now we're gonna do one in place call here. VulkanContext.inPlace. In place. vk get instance proc.addr. And there you go. Number matching for call to in place. Because we need the window too. Is that the case? Make instance. So get instance proc.addr and the window. Well, window.get. And there we go. There we go. Or if you want to, this could even go inside of that VulkanContext, and you wouldn't need this either. And you would basically say static auto make context. And we just return making it instance proc.addr RAII context. There we go. Perfect. And here, instead of getting this, could remove it and just say make context, and that should do the trick. So now we only depend on the window, and that's pretty much it for the Vulkan context. Yep, that's pretty sick. Alright, so the next thing we're gonna need is, so the Vulkan context basically contains kind of like the global kind of Vulkan things that everything else needs. But then we also need some kind of thread local things. So I'm gonna call that maybe struct thread Vulkan context. And that's gonna be stuff like the command pool and the command buffers. So that's gonna be Hpp RAII command pool and Hpp RAII command buffers. Because command pool is not thread safe, basically, and command buffers aren't thread safe, pretty much. That's why. And what we could basically do here is we could, I haven't, like, if you really need thread stuff, you could say thread local, thread Vulkan context. We're not gonna be doing threading in this first video, but maybe in another video. So thread Vulkan context. Though probably you would still wanna do an std optional here. So thread local is only allowed on variable declarations. But yeah, for now we're not gonna make it thread local. Right now, just keep it simple because we don't have multiple threads just yet, but we're preparing for that essentially. And I'm showing you why we have a command pool and so on. So like you would want a separate command pool per thread and per like queue family essentially. Right now we're not even taking care of multiple queue families. That's even crazier, but yeah. So that's pretty much it for the thread Vulkan context. We're also gonna need the swapchain stuff right now. So struct swapchain. So the swapchain would be, so it would have like a Hpp RAII swapchain, and it would have the std vector of Hpp images, not Hpp RAII image though, because we don't own the swapchain images. So we just use the regular image handles. And once we actually start rendering, we need also image views. Right now we don't need them just yet, so we're not gonna make them. So yeah, I think, what else we gonna need? I think we're good for now. Next thing, we're gonna need some resources for frame synchronization. So for frame synchronization, we're gonna need a Hpp semaphore. Well, expected after, oh yeah. So basically we're gonna need the render finished semaphore. Good luck with this, I'm going to sleep. Goodbye, Cyber Persal. Good night. Okay, so render finished semaphore, and we're gonna need, what else? image acquired semaphore, yeah. And one thing I gotta change actually here too is the tab size to 2 to match the Clang format. So Clang format by default uses the LLVM style, which uses 2 tab size basically. Though we could probably change that if we want to, let's say Google for example. Clang format Google, let's see. Come on. Let's say this. You would just say based on style Google. You could do that. New file .clang format. Now if I save this again, now we're using the Google style. Though even the Google style actually uses 2. If you want 4, then you could also change that. Though I don't remember what it's called. Let's see. Tab width apparently. Okay. Tab width 4. And now, did I miss it or what? Like Clang format tab width. Well then why it's not working? Yeah, it doesn't seem to work out. But to be honest with you, I'm just gonna stick with LLVM style, honestly. So yeah, that's pretty much it now. Let's see what else we need. So we also need the image acquired semaphore. Image acquired semaphore. Well. And then a fence. So in flight fence. So vk fence in flight fence. And yeah, that's pretty much it. So semaphores are basically used to synchronize between the GPU queues, like the GPU tasks, like the tasks that happen in the GPU, and the fences are used to synchronize between the GPU and the CPU. For example, the CPU could use a fence to wait on the GPU to finish execution, because otherwise anything that you execute using the GPU, like the CPU by default wouldn't wait, you know, unless if you actually use a fence. But anyways, so swap chain images, and we're also gonna have like a struct frame context, which would have the image index. So you int the current image index basically in this particular frame. And we're also gonna have some other stuff, but I think this should be good enough for now. Let's start by creating a thread VulkanContext here. So how are we gonna do this? Well, we're actually gonna make a constructor for it though. So private static make command pool, Hpp RAII command pool here. And for this, we're gonna of course need a device here. So to make a command pool, what we're gonna do is say device dot create command pool. And here we're gonna say vk command pool create info. And the thing is that we're gonna need here we could set the key family index, yes, later on. For now, we're just gonna ignore that. We need to set the flags. Vk command buffer, create flag bits. So we want to be able to reset every individual command buffer, so we're gonna use that flag. And of course we want to return this basically, so return this what? Well, auto here, and we're good to go. Otherwise, if you don't want to use it this way, then what you could do is say device like this, and that would also work. Whichever way you want, either using the constructor or the factory function in the device. And yeah, that's pretty much it. So here we're gonna basically say we need the constructor right now, thread VulkanContext, and we're gonna basically say, well, make command pool. It would need the RAII device pretty much, or to simply take the whole context and call it a day. Yeah, could also do that, so just say context. And that should do the trick. Now we're just gonna say command pool, but well, let's actually make sure we're respecting our conventions here, and that should do the trick. Whoops. So for the command pool, we're gonna go with the device. Well, actually we're gonna go with make command pool here, and we're gonna say, well, this is our context essentially, so and oh, let's also change it here. VulkanContext. Now here we could, wait, no, just keep that. Here we could just say context.device. And there you go. Perfect. Next up is the actual command buffers. So for those, wait. Yeah, so right now we need also another helper function for allocating command buffers. So allocate command buffers, and this would return command buffers. And this would basically be, I believe, command, well, actually device. Yeah, comma, and here we gotta go with command buffer allocate info. Well, now here we're gonna need to set the allocator though. Sorry, the command pool range. And of course we can get that here. So vk RAII command pool. Command pool. Okay. Alright. So here we're gonna pass in the command pool, and we should be good to go. Now we're just gonna say command buffers, allocate command buffers. Here we're gonna give it the context.device, and here the command pool. And there you go. And we're done with the thread VulkanContext. Perfect. And yeah, also for the frame context, we also want another thing. Well, for one, the current frame index should start at 0, And the other thing you're gonna need is should we recreate the swap chain in this frame? And by default it's gonna be equal to false. Right. Now what are we gonna do next? So other than, well, frame context, wait. We're also gonna need another struct called frame resources, let's say, which would basically contain an std vector that would hold all of our frame sync. Isn't it? Yeah. And frame sync. Frames. And also, let me fix these naming conventions real quick. And that's basically it. Now, for the swap chain, let's also implement that. So we're gonna basically do something similar to this guy here. Make swap chain. Vulkan RAII swapchain KHR, and here, oh, what the heck I'm doing? No, keep the device. And here we're gonna create the swap chain. So of course we're gonna also need, other than the device, we're gonna need the surface. So surface KHR surface, and we're gonna return a swap chain KHR. And here, whoops, we're gonna basically say swap chain create info KHR. Now here we're gonna set, of course, first of all the surface here, though we do need to get the, for now I'm just gonna hard code honestly some stuff. Like the format, let's say, image format. We could hard code that, let's say, to format unorm this guy. What else? For the image count, set minimum image count. So here we actually need the surface capabilities. The surface capabilities. So we kind of have two options here. We could either get it as a parameter or get the physical device as a parameter. And hello, Tuk Tam Duke, welcome to the live stream. I think we, for now, maybe we could just grab the physical device, in fact. Pretty much. Now, after we grab the physical device, right now we could get the surface capabilities, basically. Which is going to be equal to physical device dot get surface capabilities KHR, and here we could give it the surface, and that's basically it. Now for the minimum image count, we could say surface capabilities dot minimum image count +1. That's kind of like the best practices. Next up, we're gonna need the minimum, like, image array layers. We're gonna go with 1. I only gonna need this, like, let's say if you have, or you want to do, let's say, stereoscopic rendering. I think, like, let's say you're rendering to 2 views or whatever, then you're gonna need that. But for now we don't. Of course we also need the color space, I believe. I'm just gonna keep it as default, in fact. Set image extent. Well, we already have the image extent here, I believe, so current extent. What else? Say image usage. Currently we're just going to use a transfer command to start off to just clear the window. So we're just going to go for the image usage. We're going to say image usage just transfer, pretty much DST, destination. What else we're gonna need here? Let's see. Clipped to true. You only need to set it to false if you want to read back the swap chain content. Otherwise, just set it to true for performance. What else? I think that's pretty much it. There's image sharing mode and stuff. We don't need to touch that because we're using one queue family for now. There's also alt swap chain. We don't need that. The other stuff, we could just keep them as default, pretty much. Yeah, let's just keep the others as default. And that's basically it, I believe. Yeah. So after we create the swap chain, well, honestly, we could create it here. Or, yeah, nah, just keep it, really. And after we create the swap chain, we can get the swap chain images. So right now, let's create a swap chain kind of constructor here, where like we set the swap chain to make swap chain to, well, first of all, let's grab the context essentially, VulkanContext. Context, and of course a reference to the context. So here we're gonna say make swap chain. So for the device, we're gonna take it from the context, and the surface, same thing, context.surface, and here context.PhysicalDevice. And we're done with that part. Next up is the swap chain images. Now, well, what the heck? Now for the swap chain images, we're gonna say swap chain get images, and there we go. Whoops, this should be RAII. And there you go. We have done the swap chain, I think. So now for the swap chain, we could just create another std optional here for the swap chain part. And yeah. I think that's basically it. Frame sync. Let's do the same thing for this guy. Let's see. So private, and we can just copy this part, for example. This time, instead of make swap chain, we're gonna have make semaphore, and like you just gotta take the. You're only gonna need the device for this. And here we're gonna give back a semaphore. And we're just gonna return vcase, semaphore, create info. And that's that. Expected for functionals. Oh yeah. Well, let's add that there, and we're good to go. Honestly, this is very simple that we don't even need construct like static stuff. Well, yeah, that's true. What we could do, we could just say frame sync, and here of course we're gonna need the VulkanContext. And here for the image acquired semaphore, we're just gonna give it the context device and nothing. Render finish semaphore, same thing. Context.device and just default. In flight fence, on the other hand, it's not gonna be the default. We're gonna take the context.device, but here we're gonna give it the vk signaled. What is it called? Fence create flag bits signaled, and hopefully that does the job. Maybe we do need like a vk semaphore info thing here. Well, what create semaphore create info. Well, actually, I think I know what's the problem here. I forgot RAII here. Pretty much, that's why. And there we go. Perfect. I think that's basic. Though I do remember some problem with that thing, honestly. Let's just give it that. Yeah. Otherwise it wouldn't construct it properly. It would keep it empty. Yeah. I see. And that's pretty much it for the frame sync. Frame resources. Okay, so for this one, I'm gonna have a static helper. Like for example, this guy here. Paste. And instead of allocate command buffers, this would be, let's see, make frames. And instead of, we're only going to need the device and how much in flight frames we're going to have. So uint, or just size t, in flight frames count, kind of. And then what we're going to do, we're going to basically return a std vector. And for that, we're going to basically create a vector and then go through in std views iota. Yep. Flight frames count, and then gonna basically say frames dot in place back in flight frame count. Now of course we're gonna need some header for this, include ranges, and there we go. We're not gonna need the index. We're pretty much this is kind of like a raw for loop. It's just more declarative. So like basically we're gonna push in like frames n times essentially. That's basically it. So std vector frame sync. Now we could reserve that stuff. So like reserve. Wait, what? There we go. In flight frames count. And there you go. Whoops, well, we gotta give it the context here. Well, actually, yep. So instead of device here, let's grab the context. VulkanContext. And finally, let's return frames. And I think that's all for that part. Now, frame resources. Of course, we're gonna need the context and in-flight frame count. And then we're gonna say frames, make frames, the context, and then in-flight frame count. And that's pretty much it. Wait. Does not name. And we're good. And there you go. That's a lot of crazy stuff. So the swap chain, and we have the frame resources. CD optional. Frame resources. And SCD optional. Well, honestly, for this part here, we don't really need a CD optional. It can default construct the frame context. The frame context is basically what changes from one frame to another at runtime. And frame resources, swap chain, and yeah. Alright, let's see now how we could construct these. So after creating the VulkanContext, we could create the thread VulkanContext by emplacing. And let's see what the thread VulkanContext requires. Thread VulkanContext. It requires the VulkanContext too simply. Well, of course, let's dereference this. And there you go. Next step is the swap chain. What it requires. Let's see what the swap chain requires. The context too. Perfect. So, context. There you go. Next up is, what else? The frame resources, I think. Alright, so honestly, I would create the swap chain maybe after the VulkanContext. For the frame resources in place, and what that needs, it needs the context and the in-flight frame count. So the context, how are we gonna do that? VulkanContext, and here we could say, let's say 2 frame in-flight frames. And what else? Frame context, we could just initialize it, and there we go. And I think that's pretty much it, I believe. Is that it? Hello. What's up? So we have the command pool, we have the command buffer, we have the semaphores, we have the fence. Do we need anything else? I don't think so. Alright, that's pretty cool. Pretty cool. So let's actually do something like this here. And we don't need the SDL log here. And I'm pretty sure we don't need these. What else? SDL main. Every time I watch your video, I learn something new. Yeah, I'm always trying to learn something new. So for sure, any video you watch of my content, you'll definitely learn something new. Because I'm really into shiny objects. But yeah. Here, instead of having these, we could just say like SDL directly, in fact. Yeah, I think so. Though here for the external headers, please let's use these instead. Same thing with the others here. And there you go. Perfect. Do we actually need all these headers though? Do we need all these headers? Well, I don't know. Oh, definitely not this guy. There you go. So far, I think we're done with the initialization stuff. I should have compiled this stuff before, but well. Okay, so let's see what's up with this guy. I'm pretty I think I know where this is coming from. It's definitely the extensions. Yeah, the swap chain. Ah, yes, I see. I know exactly what's going on here. So this apparently should be, I guess, its own array. So extensions essentially. So required extensions here. And we're basically going to say cd array required extensions, and I think that should work now. Alright, what the heck is going on here? In the find reference to oh yeah, I should make sure to also have include SDL3 main here. I removed it by accident. Let's try to run this now. Oh, what? Out of device memory error, what the heck? Oh, width and height. Out of the, hopefully it didn't F up my, oh my god. Is the stream fine? It seems fine. Because I tried to allocate all this GPU memory. Alright, well. So I forgot that I'm on Wayland, so that wouldn't work. How are we gonna fix this? Well, let's go to make swapchain function. Make swapchain. Let's see. Alright, so here we're gonna need to set the image. Well, in fact, we're already doing that here, right? But it shouldn't use the current extent here. It should use from SDL. So the width and height from SDL. Okay. So we're gonna basically do this, and then we're gonna say integer width comma height, and then we're gonna basically say if not SDL get window size in pixels window. Well, do we have the window here? Well, we do have the surface, but I don't think we have the window. Well, we're gonna need to get the window then. Width and, or honestly, instead of that, we could just take the width and height from the user, or well, from the caller, instead of taking the whole window. But a lot of crap. Well, let's just keep it honestly here. I don't care. I don't care. Let's go. Let's just keep it there. Okay, so if that's not the case, then we're just gonna throw SDL exception couldn't, well, failed to get window size for whichever reason. Alright, so here we basically need to make sure that we also get the window apparently. And that should do the trick, I think. Well, let's remove this. And we're good. Now, make swapchain, who's calling it here? So let's give it the window 2 apparently. And well, SDL window. And there we go. Alright, so now in fact when we create the swap chain, we gotta also pass it the window. Alright, window.get. Okay. Let's try this now. Oh yeah, I need to static cast that stuff. Control dot insert an explicit cast. Control dot insert an explicit cast, and we're good to go. Run. And yeah, the initialization seems complete. And when you quit the application, everything gets destroyed in order. Perfect. Let's make sure there's no validation errors so far. There's one though. The command buffer count. Oh yeah, forgot that part. So allocate command buffers here. So I set the command pool, but I didn't set how much command buffers we want. Apparently. Yep. Okay, so here we're basically gonna say command buffer count. Well, this is basically how much in-flight frames we have. And we're basically gonna include it here, right? So what this takes, I think it probably takes you in 32 though. Right? Yes, it does, I think. Well, probably. Either way. So here, when we create this guy, we also need to take in 32 this in-flight frames count. Well, honestly, let's call this in-flight frames count instead. And here we need to pass in flight frame count. Righty, and that's pretty much it, I believe. But wait, hold on. If we go to swap chain stuff, do we actually need all that crap? Hold on. Well, actually, we're already passing that. Yeah, we're already passing that stuff. Never mind. Alright, so is everything okay now? No validation errors? Well, we forgot one little thing, which is here. We need right now to pass in the actual in-flight frames count. And since we have it in multiple places, let's make it an actual variable. In-flight frames count. Well, honestly, let's make it a constant. In-flight frames count. There we go. Weird. Honestly, let's just, I guess, hard code it for now. Wait, what's happening there? Weird. For some reason, whoops. Thread VulkanContext is not accepting that. Can we make this size C instead, please? And then here, maybe size T. But why this is having a problem? What the heck? Oh, it was just an old thing. Old error. Okay, never mind. So right now we have no validation errors in terms of initialization. Right now we need to get into the actual event loop. Well, not event loop, but like the frame, right? So the first thing, of course, we need to do is to, let's see. First of all, we need to wait for all the fences to finish. So well, not SDL, but like, so VulkanContext, I think. Context. Well, wait, what? Device, right. Wait for fences. So we will basically wait for, well, we need to first of all grab the current frame. So auto current frame is equal to essentially frame resources, frames, frame context, whoops, dot current image index. Well, not current image index, but like frame index. Yeah, where are we gonna put that? Good question. Good question. Where to put that? I would guess the frame resources, pretty much. Yeah, definitely. So yeah, let's put that there. What are we gonna say here? Size C frame index, or like current frame index, I guess. Yeah, perfect. And of course, by default, like, it would be equal to 0. Right. And then what we're gonna basically do, we're gonna actually have, Walaikum Assalam Abdul Rahman, welcome to the live stream. The next thing we're gonna have is like get a frame, right? So frame sync, well, essentially auto, right? Get frame, which is basically going to give us a frame sync reference, and we're going to return frames dot get, well, actually not frames dot, frames dot add, I think, at current image frame index, right? Expected a type, huh? Yeah, like this. Okay, cool. Frames at current frame index. And actually, before we return that, we're gonna say current frame index is equal to current frame index. Well, wait. Current frame index plus 1 modulo frames dot size. Whoops. Like this. So it's kind of like a circular cursor or a circular buffer kind of thing. So if like we have 2 frames, then it's going to be like get the first frame, second, we're done, let's get the first frame again, and so on. That's what the modulo does here. And yeah, I think that's basically it. Though I'm still gonna need the current frame index for other stuff, like the, actually no, I think that's it. No, yeah, I think that's pretty much it. Lovely. So okay, cool, love that. So how are we gonna do this now? We're gonna say frame resources now dot get frame, and that's basically all we do. Cool. Or to be even more exact, we can rename this to, let's say, acquire next frame. Too simply. Just like the acquire swapchain image thing. Right. So now the fences. So the fence is going to be, of course, the current frame dot in-flight fence. The bool 32 wait all, we could say true, it doesn't matter in this case. And for the timeout, let's just set it to the maximum. So numeric, I think, or numeric limits, yeah. UN 64. Though this is basically requires a vacay fence, but this is the RAII version, so we need to dereference it essentially. And what else? Dot max, we need to get the maximum there. And of course this returns some error stuff that we're just gonna ignore for now. And that's basically it. We're gonna wait on the in-flight fence. After that, we're gonna check. Well, actually, we're gonna acquire the next image. And for that, what we're gonna do? So, so it would basically give us an image index, and it would give us the result. Well, in fact, I think like this maybe. Image index is equal to well, is it the swap chain? Yeah, acquire next image, and then here the timeout, pretty much the exact same thing we've done here. And yeah, that's perfect. Now the thing is, if the result is equal to vacay, let's see, well, result, right, right, suboptimal, and there's another one. What is it called? Out of date, I think. Swap chain. Wait, what the heck? Bruh. Why? Wait, what? Oh, okay, so some weird crap happening here. Let's remove that. Honestly, you know what? This would always suck. So what I'm gonna do here, I'm gonna basically define these in my CMake list instead of having it there, to make sure it is included everywhere, so I don't have to remember the order and so on. So how we can do this? Well, target compile definitions, the target name, which we're just gonna go with project name here, private, and what else? So first of all, we're gonna have this equal to 0, and we're gonna have this, and we're gonna have this. And that's basically it. Now we don't actually need all this crap, and we're good to go. Perfect, lovely. All right, so let's continue what we were doing before that compile errors storm. Okay, so we got the acquire next image, great. So now we basically need to check if the result is equal to vk result e, well, out of date, right? Again, what the hell is wrong with this guy? Oh my god, it's still trying to do it. Oh my, this auto includes will kill me, dude. Ah, so annoying. Anyways, where we were. Yeah, it totally threw me off. Oh my god. There we go. Please don't do it again. Equal to vk e, well, result error out of date khr if result is equal to that, or result is equal to vk result e error, well, suboptimal, I think, or actually suboptimal khr, right? So if that's the case, then for now, let's just say return SDL app failure. Or so basically here we're supposed to kind of like recreate the swap chain actually. So how are we gonna do that? Well, I think we could probably just create a new swap chain. So to create a new swap chain, you need the context and the window. And you just swap it. And that's basically it, I think. And then of course we're gonna need to return SDL app continue. If we're good enough, if we don't recreate the swap chain, then we're actually gonna go ahead right now and reset the fences. So like VulkanContext device.reset the fences. So frame or current frame in flight fence, right? And of course that's video reference this, and there we go. Okay, perfect. Do we even need then recreate swap chain? I'm not sure. For now, let's just remove it. Oh, current image index. Huh, interesting. Well, honestly, for now, I think I'll just ignore the frame context for now. Remove it. Thank you. And let's just keep this simple for now. Okay. I mean, it's not that simple, but anyways, all right. So we acquire next frame, and we then wait for the fences. Then wait. Then we acquire the next image. Then we reset the fences. Now we could actually start like recording to the command buffer. How are we gonna do this? Well, where the command buffer resides, I think in the thread VulkanContext, right? So the command buffers. Oh boy. Well, here we actually gonna need the frame index. So that means the frame resources do need to give us that after all. Okay. And how it's gonna do that is by simply saying get index frame index, and this would essentially return size C and return current frame index, I guess. Now here what we could do is current frame, well actually frame resources get frame index, so this is like the command buffer here. So let's make sure this is a reference. And that's basically it for that. Now let's actually say command buffer dot, hold on a second. Alright, so first of all we need to reset it. So reset vk command buffer reset flag bits. Now we don't need any of that, so let's just keep it that way. And then can we actually just chain this? No, we can't. Okay, so command buffer to begin, isn't it? Oh my god, don't tell me that crap again. Oh my. I really hate this. I truly hate this. I mean, it's supposed to not do that crap. I am passing this crap, but well, anyways. Command buffer dot begin. So now vk command buffer info. Please don't tell me did it again. Probably did, yeah, I did. Alright. Can't do shit anymore. Anyways, set pnext, p inheritance info, set flags, set pnext. We don't need any of this, I think. Maybe set flags. Is there anything there? So E1 times submit. There we go. And finally we need to say command buffer dot end. And there we go. Is that it? So begin and now we could actually, like, you know, do command buffer dot clear color image. And here we need to grab the image. Okay. Well, the image would be is equal to swapchain dot get images dot add image index. Or can we just say image index like this maybe? What the heck? Oh no. Images, swapchain images, image index. There you go. Or we could say .add image index like this, I think. There you go. How about if I don't give it? Nah, never mind. Alright, so that's pretty much it for that. Now we could just say image, well, not that, image like this. Now the image layout, color attachment optimal. Well, we're gonna go with, wait. This needs the current. Okay. So here we're basically gonna say image layout transfer DST. That's the optimal layout. And they probably did that bullshit again. What if I just include Vulkan / Vulkan.hpp, and hopefully it wouldn't include shit anymore. Really sucks. It's pissing me off so badly. Please, can you clang the restart? Well, because this is wild. Transfer DST optimal, yes. Next up is the clear color value. So basically color, and then the image subresource range. Image subresource range dot. So here we're gonna need, of course, the layer count. Well, wait, set layer count 1, set level count 1, and then set the aspect mask to vk aspect mask, flag beds to color, and we're good to go. Now the color is basically vk clear color value color dot set float 32, and here we could set a color like, let's say, red. Though I believe we could probably just say vk clear color value. Yeah, we can, so that's cool. So we could remove that crap, and yeah, that's pretty much it, I think. So we cleared color image, then of course we need to submit this command buffer. How are we gonna do this? Well, through the VulkanContext.q, they'll submit, and here the submit. So vk q submit, well, submit info, right? Dot set command buffers, command buffer dot set wait semaphores. So it should wait on the image acquire. So basically frame current frame dot image acquired semaphore. And oh, well, we forgot about that here, I think. Well, not here, here. So the fence should be, well, the semaphore first. Yeah, so current frame dot image acquired semaphore, too simply. And then here set wait semaphore dot set signal semaphores current frame dot image acquired. Now here render finished. Though after the submit is done, please signal the fence. So current frame dot inflate fence. Too simply. Though I'm pretty sure that this is RAII, so we basically need to kind of dereference them, I think. Though let me just show you, it's probably gonna error out right now if I run this. Either way, after the submit, we can like present this. So how are we gonna do? I don't think we could do it through the swap chain, I believe. So yes, no. So let's go ahead and go through the queue, of course. So present khr vk present info khr. Of course, I'm still missing some synchronization stuff here, but yeah. Now set p image indices before I forget about that. Image index dot set swap chains 2, please. Set swap chains. Swap chain dot swap chain. Whoops, swap chain. Though I'd rather like the swap chain first, honestly. That makes more sense in my head. So yeah, so set swap chain, set image indices, and right now set wait semaphores. So for the semaphores, we're gonna wait on the current frame dot render finished semaphore. And is there anything else we need? Pretty much no, I think. Yep, no. Nothing else to do there. And for this, what we're gonna do is if result, well, basically let's say outlaw result is equal to that, or to simply say result like that, and just do the same thing again. And yeah, though actually not here. Here we should just set that recreate. Yep, I think so. Yep, that's what I'm gonna do. Or honestly, we could just ignore that for now. Pretty much. We could return SDL app failure. Right, and then, yeah, for now at least. And let's see. Of course, this wouldn't work. It would error out. And it's because we're passing in RAII stuff. So how we could fix this? Well, I'm gonna basically dereference all of those. Here, 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 here. Is that it? I mean, I think so. Let's try. And there we go. The only thing left is pretty much to just make sure that we do the proper like synchronization. And to do that, well, I just to simply say command buffer dot pipeline barrier. Now the pipeline stage flags. So for that, we're just gonna say vk pipeline stage flag bits to e transfer, because currently we only have transfer commands for the DST. But wait, yes, pretty much. For the DST stage mask, same thing. Dependency flags, we don't care. The memory barriers, we don't care. The buffer memory barriers, we don't care either. The image memory barriers, though, we do care. So what we do care about here is, of course, first of all, the image. And then we care about the new layout in this case. We want to make sure that the new layout is vk image layout e-transfer DST optimal, basically. Well, of course, set new layout. Yep. And what else? Set DXT access mask. So vk access flag bits. We're gonna say e-transfer write, because we're gonna basically write to the image using the transfer command, which is clear color image. And that's basically it for that part. Now we're just gonna basically, well, am I missing something else? Let me see. Not really. Well, actually there is sub-resource range, yeah. Okay, sure. We're just gonna copy the sub-resource range that we set it here. And there you go. Now I'm just gonna copy this pipeline barrier after the clear color image here. And we're gonna basically do, so this is like the, instead of new, the new would become the old, the DST would become the SRC, and we're good to go. Now we do need the new layout to set that, so set the new layout to image layout present KHR, and we're good to go. And maybe the DST access mask. Well, honestly, let's just keep it empty for now. And yeah, pretty much. So this should do the like image layout transitions. And yeah, we still have all sorts of crazy semaphores, like synchronization stuff to fix, apparently. Oh, p-weight DST stage mask, I forgot about that part. So where is that? I think probably here somewhere, maybe. Set p weight. Yep, exactly. So, alright, sure. Weight DST stage mask. Pipeline. And there we go. No viable conversion. There we go. Can we clear this? P signal is being signaled by still being used by. Yeah, we need to use the VKHR maintenance extension. Pretty much. That is what's left, though I think I'm gonna take a break and then I'm gonna come back. Okay, we're back. Okay, so how are we gonna do this? Well, there's no way out, I think, other than basically using this VulkanContext maintains one extension. I'm not sure if this is like a new thing or like in Wayland it's more strict about this stuff, but yeah. Alright, so let's do that. So how are we gonna do this? Well, we're gonna add another fence. This would be our present fence. This would tell us when the presentation is being done. Right, so we're gonna just copy and paste this. But of course, this is gonna be our present fence. And after that, or to simply go into in the submit info, I think, or nah, wait, the present info. Let's check it out. Wait. So swapchain maintenance one present fence. Well, extending vk present info khr, there we go. So we basically need this vk swapchain present info khr. So this is what we need. So how are we gonna do this? Well, I think we need like a structure chain or chain structure, or what was it called? Well, vk structure chain. There we go. And I think basically need this, comma, vacate this, and like this would be the actual present info, or present chain if you want. And we could remove this from here and just say present chain dot get the vk present info khr, and then here we could say honestly, yeah, and we could just say directly set this stuff. Other than that, here we're actually gonna get the oopsies, wait, present chain dot get the vk present, well, the swap chain present fence info xt, and we're gonna set the fences right there. Well, first of all, we got the swap chain count apparently, and then we need to set the fences. Though, do we really need? I don't think we need that. Maybe it would just infer from the fences here. Yeah, probably. So here we're just gonna say frame resources dot, well, actually not that. Current frame, yeah. Current frame dot present fence. Now, of course, someone has to wait for this present fence, and that someone is our wait for fences here. We're gonna, instead of giving one fence, we're gonna give multiple fences. So we're gonna also give the current frame dot present fence. We're gonna make sure that it waits for all of them before proceeding. And that's basically it. Well, dereference this. Let's go. Okay. And boom. Must be in signaled. Wait, what? Let me try to clear this first. We need to actually enable swapchain maintenance. And to enable swapchain maintenance, that's gonna be interesting. So we kind of need to essentially extend the device create info with this guy. Yep. So let's do that. Alright, so where's the device info? Where are we creating the device, dude? Here we go. So we got the create info here. Okay. So here we're basically gonna have a chain. Structure chain. Well, what the heck? And chain. And of course this chain would be like this, vk. And there we go. Now this chain, again, same thing. Dot get vk device create info. And then to simply chain dot get. We're gonna get this feature struct, and then we're gonna basically set the swapchain maintenance to vk true, and there we go. And that's how you enable a feature. And let's see. Now let's reset, let's clear this and let's see what's up. Oh, we're not resetting it. Okay. Reset fences. Well, same story here. Current frame dot present fence. Now, if we run this, let's hope for the best. And yeah, we're not getting any synchronization errors anymore. If we clear this and try again, look at that. We're finally getting a proper window with no validation errors. And even the swap chain gets recreated, though there's one little side problem. Well, actually it doesn't allow it. So you have a minimum height, but like if it was able to go to 0 by 0 dimensions, it would have sucked. But yeah, it actually works out flawlessly. Look at that. Perfect. And no errors at all. Am I right? Are those errors from my... Yeah, well, one last piece actually. In the SDL app quit, make sure... Well, here actually in quit. Make sure to... SDL... Well, not SDL, like... basically the VulkanContext.device.GPU wait idle, or like wait GPU idle. Whoops. to make sure that we wait for the GPU to end all operations, then we can deconstruct everything, so we don't have those errors in the deconstruction. Essentially, like if we clear this, run, close, there you go, no errors even in deconstruction. And yeah, we have done it. How much time it took? Well, for everything, 3.5 hours. Remove the half of the IDE setup, and you got 3 hours. And yeah, that's pretty much it. You're definitely gonna find the link down in the description below after some time, maybe a day or two. Please join my Discord server. I'm going to, like, once I publish the repo, you can find the link down in the description. So what we have done, just to recap, today we only have made a clear window sample using Vulkan Hpp RAII, you know, and yeah, that's using, of course, Vulkan 1.4 with the swapchain maintenance one. And yeah, that's pretty much it. Thank you all for watching, and see you in the next one. Goodbye, everyone.